here today. I'm going to introduce them real quickly, and then I'm going to turn the program over to them. We have Mr. Steve Piltz with us today, who's the Chief Meteorologist with the National Weather Service office in Tulsa. And we have Mrs. Nicole McGavick, who's a hydrologist with the National Weather Service office here in Tulsa, and they're going to talk to us a lot about meteorology and science today.
Thought we'd talk about tornadoes today. That's what the STEM folks thought would be a good topic for you guys, and talk a little bit about how things have changed, how technology has changed, and how we deal with tornadoes have changed over the years. There's been discussion over the last 10 years. The big tornadoes don't hit Tulsa. They hit everywhere else. But you know, the last 2 or 3 years, we've had strong tornadoes somewhere in or around Tulsa. And there's no reason that a stronger tornado won't hit Tulsa at some point. So it's very important to talk about this and not just get into the idea that, well, it doesn't happen, because actually it does. I mean, we're right in the middle of where we would expect to see tornadoes. And so let's talk a little bit about some of the tornadoes in Tulsa's past, and then some of the things we're doing in technology that just tries to make things a little bit better. First, I wanted to just basically say we're from the National Weather Service. I know most of your idea of the National Weather Service is the words that scroll across the bottom of the TV screen. Whatever station you guys like to watch when the weather gets bad and stormy, you see that the National Weather Service has issued something. That's who we are. We're the people that cause the little text to go across the bottom of your TV screen. We're a part of the federal government. We're responsible for the forecasts and warnings in eastern Oklahoma and northwest Arkansas. This is a shot inside the Tulsa Weather Office. It's one of those panoramic shots that I kind of broke in half. So the top image is going from left to right, and the bottom image picks up where the top and left off and continues on. So you can see lots of computer screens, lots of things going on, lots of reason to study math and science and computers if you're going to be a meteorologist or have anything to do with earth science or anything that has to do with forecasting the weather. Nicole can attest that it's something, if you think you like meteorology, one of the things you also need to like, or at least be able to do, is math. Math is a big deal. We're in the same classes as the engineering students, the med students. Anybody that's getting into the higher level math, you get into that in meteorology as well. It's not that we have to make all those calculations every day, but we have to understand where the calculations come from. So it's important, as anybody in the room that thinks meteorology is something they want to get into, that's something to make sure that you, at least what I finally learned, because I'm not very good at math, what I finally learned was to do the homework. If you do that thing where you do the first 2 or 3 problems of your homework and you think, oh, I pretty well got this, you got to do all the homework, because it's always the homework at the bottom of the page that shows up on the test. And once I figured that out, I actually started to at least understand math a little bit better. So you can get through it. If you love weather, don't let the math stand in your way. You just have to work hard at it and just get through it and do it. This gives you an idea of the Weather Service structure across the United States. The Tulsa Weather Service is part of a network of weather offices that are 122 across the country. That also includes Alaska and Puerto Rico and Hawaii, even some of the Pacific Islands. So there are weather forecast offices scattered around the country. Obviously, Tulsa takes care of this area. Norman is the weather forecast office to our west. We have Wichita and Springfield and Little Rock, Shreveport and Dallas-Fort Worth, all ring the area around our office. This is our forecast area. If you're ever here to hear National Weather Service in Tulsa, it's not just a Tulsa thing. We're responsible for the forecasts and warnings in 32 counties. It's mainly kind of around our radar coverage. What do our radars cover best? And so those are the counties that each weather office takes care of. So let's talk, now that you know a little bit about the Weather Service, let's talk a bit about tornadoes. And again, this idea that Tulsa never has the big ones. Well, part of the idea that sometimes we have of that is some of our tornadoes that we've had in the area haven't hit things. And the way we rate tornadoes is through what scale? Do you guys know?
Yeah,
the Fujita Scale. Ted Fujita, he was a young man in Japan, and he was studying basically STEM stuff. He was studying meteorology and science, and he was there when the atomic bombs were dropped. And he saw the damage pattern of the bombs, and eventually he related some of that to some of the storm damage we see in thunderstorms. And so his focus really began to really be on how thunderstorms, and particularly tornadoes, damage things. And so he took some of the tragedy that he saw in his home during the war, and he then evolved that into something that we use all the time in springtime. We have the Fujita Scale. It was enhanced a few years ago because construction changes. Things that Fujita developed back in the late 60s and into the 70s are a little bit different now. We build our houses different, we build our cars different. Our cars are lighter and smaller because we want to have better gas mileage. And so those are different. And the way we build our houses are different. So what Fujita developed was a scale for us to walk around and look at houses and things and how they're talked about in storms and say, okay, that should have been a wind, say in this range, 80 to 90 miles an hour. That should have been a wind of 100 to 120 miles an hour. So based on the principles that he started, that's what we have now as the enhanced Fujita scale. So you can see the numbers there. You can see how they changed from his original scale back to what we have now. There's EF0 through EF5. Technically, he did actually continue the scale all up to the speed of sound, but there was no expectation to ever use F6, 7, 8, 9. I think it goes up to maybe even F12. I forget now. But technically, operationally, we don't use anything beyond F5. Anytime that we believe a tornado's produced winds above 200 miles an hour, that's considered an EF5. The tornadoes, as they happen, they're all different. You can't. Sometimes I think people believe that, well, there's a tornado coming, so they're all the same. They're all equally bad. And actually, they are different. If it's EF0 or EF1, EF2, if you've taken appropriate shelter, you're probably going to be okay. If you've ducked through the EF0s, EF1s, EF2s, even into EF3s where you really start to see a lot of stuff tore up, if you had enough warning and you could duck and your house was okay, you can get to those safe spots that they teach you all about during springtime. EF4s and EF5s are harder though. EF5s and EF4s bring down well-built houses. Those are the tragic things that we see sometimes in the springtime. And those are the types of storms that are the kinds that really destroy big chunks of communities. Let's walk you through EF scale rating just a little bit. You guys can be the raters on this. This is let you guys decide what's going on here, give you an idea a little bit where these EF ratings come from and how we do these things. This is tore up. You guys agree that that's tore up? We're all good with that? This is a metal building. In fact, this is what it rust. Why would the bolt rust in the middle? I mean, that was supposed to be a solid metal bolt. Water got in there somehow, so something was wrong with the bolt. So now we have more evidence to say, hey, you know what? That wasn't 155 mile an hour wind. Somebody built that building to really good specifications, but they used bad bolts. How do you know if you're buying bad bolts at the hardware store? You don't do that. But they're rust, yeah. So now we know we can go back and look at this. Instead of having this being rated something really high, I think we rated that area more like EF1 to EF2. It wasn't, something was wrong. And so as meteorologists, we came out there, we did exactly what you guys did. The trees are standing, they still look okay. There's a building over there across the street that's not tore up, something's not right. So we dug a little bit further into the building and sure enough, we found the clue we need. So we do that a lot. We walk around the buildings, we walk around areas trying to get ideas of what we think happened there. So when you look at these maps like this is the map of all the F and EF3 to 5 tornadoes from 1950 to 2015. When you look at maps like that, that shows you that we've had lots of strong tornadoes in and around northeast Oklahoma, in and around Tulsa. This zone really between Oklahoma City and Tulsa is pretty ripe. There's lots of stuff that goes on there. But when you look at that map, know that those ratings are based on going out and looking at damage and looking at things. Well, what if you have this? How are we going to rate this tornado? Yeah, I mean, who knows? It looked really bad on radar. We drove. This is Osage County, so we got out in Osage County up northwest of Tulsa. We knew it. We were really sure looking on radar there was a tornado there, but. So how do you rate it? Yeah. Go ahead.
You can't really tell because it's flat land, so something really bad could happen, but there aren't any trees or buildings to assess the damage.
That's true. So now you're kind of left stuck. So we have a lot of open areas. So we can. What if an F5 tornado went across that field?
It wouldn't have done anything.
Unless you could find, you might be able to find where the grass was damaged. In really violent tornadoes, that you can see where grass is pulled out of the ground. But is that enough to call it an F5? Not really. So sometimes we hide very strong tornadoes in our area. Sometimes we get the impression like, oh, well, we only have EF1s and EF2s around here. Sometimes we have EF really bad stuff. We just don't know what it is. Nicole one time was in Osage County. She took the iconic picture. I should have brought that.
Traumatize them.
Yeah, there was a cow that did not fare very well in the storm, and she brought back the picture like, oh, it wasn't a good picture, but it was still other ways to try to figure out what was going on with the storm. So when we talk about storms, we talk about what kind of weather we have. A lot of it's based on what did it hit, and so if we have a storm that didn't hit as much, we can't rate it quite the same. Take a look at Tulsa. This will be a little bit hard to see. This is 1984, and this is 2016. If you look around a little bit, so I think I can probably, it's easier maybe to make the cursor move. Look at like where the cursor is. What do you see? What's the difference there?
It's a lot greener.
A lot more buildings there. Tulsa has grown a lot. Yes, sir.
There's more areas where the tornadoes will hit.
Well, there's more things for the tornado to hit. That's right.
There's the white, random white lines.
Yeah, those are high.
Those are hollow areas that go down under.
Those are highway markers and county lines and stuff like that. So that's just a picture. That's off of Google Earth. That's just a Google Earth thing. Yes. Yes. Go ahead and in the yellow. Yeah.
Wow. In 1984, there looks like it's a little bit more color.
There is. It looks like. I mean, they were both taken in December, so it doesn't have anything to do with the trees. It may just be more just how they took the picture. I don't know.
Maybe the green stuff is like grass, and since they built more buildings, there's less green.
Well, that's true. I don't know if you guys can hear. She says it looks like there's less green in the one picture. And that's because we've covered it up with buildings and concrete and roads. And so the idea is that we've had tornadoes in Tulsa that were pretty bad that went through some of these areas that didn't have a whole lot back then that do now. So if we had the same storm repeat, it would be a much bigger deal. There would be a lot more potential for things to hit. And so as things evolve. Yes, sir.
Are you going to talk about the one that just recently hit 41st Street?
I am. Yep, I am. So here's one back from June 8, 1974. This was a bad day in Oklahoma. Here's a tornado that really wasn't too far from here if you look at the map. It went across middle into eastern Tulsa. Notice it went right into that zone that's a whole lot different now. Would this have been rated more highly at some point? If there was more things to hit, there's a chance. So just keep in mind that as you look at these things, you have to rate them on what's there, and we change. It's the same day. These two tornadoes actually happened at about the same time. Another tornado that real close to here that runs out of Creek County through middle Tulsa, then curls on up towards Claremore. There were a couple people killed in that tornado. It was rated F3, so it was a strong tornado. It was bad. But that just to show that we do have strong tornadoes that historically have come right through the middle of town. Just thankfully they don't hit every day. If you guys, some of you guys can calculate this, maybe even yet, I don't know. I know this is a very smart room. But if you took all the tornadoes and tried to figure out what the chance of just this one piece of land being hit in Oklahoma, even though we're very prone to tornadoes, it's down less than 1% for any one piece of land. But yet, we know that they hit things all the time in the springtime, and really any time. We have tornadoes. We've had bad tornadoes in December. We've had them year-round in Tulsa. What the radar looked like. This was on that June 8th day. This is back around Oklahoma City. It's an Oklahoma City radar. But this is what the meteorologists back then were looking at, technology-wise. It was just really trying at the beginning of starting to show radar on television. This was from one of the stations down there. Mike Smith was a young meteorologist at one of the Oklahoma City TV stations. So this is not at all what you guys see anymore on TV. And some of you guys probably have radar apps on your phone where you can look at stuff. This is just very basic radar. This is just sending a pulse of radar energy out, and some of the radar gets returned back to the system. Some of the radar energy comes back based on what it hits. And so that's just a very plain look at the storm. On the notation here, you can see what's referred to as a hook echo. It's very hard to see, but notice how that white kind of comes around like that. That's because there's very strong rotation with the tornado right here, and some of the rain and the hail gets pulled around that rotating storm, and it makes what the radar meteorologists call a hook echo. So those types of storms stand out some on the radar. We'll see some storms here in a little bit that don't stand out so much. The map on the right is how we did damage surveys back then. You pulled out an Oklahoma map, and with a pencil you drew stuff on it. Now, how would you think you might track tornado damage? How would you mark it? Well, yeah, computers, that's right. Right now we carry iPads that are connected to the internet. And what kind of things are we doing? Yes, sir. Yeah, that's what we have. With our iPads, we can come up and we can take a picture of what was hit, and then we can compare that into our database of objects and things, and then we can make a rating for it. And so we're using GIS types of things. You guys do any GIS kind of projects or anything like that, where you map things and put lots of data? Anytime you're taking data and referencing it back to a map, it's some form of geolocating information. So GIS systems are really becoming more and more important in how we deal with gathering weather information, because really all weather information comes back to being information that you can plot on a map. So that was back in 1974. Let's talk about last year's tornado. I wanted to just talk to you about the tornado that hit in North Tulsa back last March 2016. This was a day that it was a very hard weather day. The June 8th, 1974. We all expected storms. Everybody knew there was going to be tornado storms that were occurring in Oklahoma that day. That was something that was going on. Back last year, it wasn't thought to be a tornado day. In fact, a severe thunderstorm watch comes out for parts of the area, but not including Tulsa. So Tulsa's not even in the watch. It's kind of just one of these days. We're going to have storms. It doesn't sound like it's going to be a big deal kind of day. Well, that's looking at just the overall weather data. But when we can begin to dig in a little bit, we can actually begin to look at things on a finer scale. Back in 1974 and the years that followed, we were looking at things mainly on a regional kind of scale. Now with computer technology and being able to get observations and get information from around the region, we can sometimes dig out environments that are going to be favorable for tornadoes in small areas. And sometimes we can't, but sometimes we can. On this particular day at 5 o'clock, you can see there's nothing going on around Tulsa. Tulsa's quiet. Earlier storms have used up the energy in the atmosphere, and so there's just nothing happening. And so the thought was, Tulsa's probably going to have a quiet evening. It's probably going to be okay. So what do we mean by energy in the atmosphere? Let's talk a little bit about that. This is where the complicated math starts. Actually, it's just quick multiplication and addition, but I told you I struggle with math, so you guys are going to have to do all the work here. The environment that I have set up is normal for like a spring day, where at 9,000 feet the temperature is 41 degrees, 6,000 feet is 56, 3,000 feet is 68, down near the surface it's 85 degrees. That's what the left number means. The right number is what we call the dew point. The dew point is the temperature that if you just suddenly took the air right here and cooled it down to where you began to get 100% humidity, that's the measure. That's what we would call the dew point temperature. And so when the temperature and dew point are closer together, the humidity is closer to 100%, and there's more moisture in the atmosphere. So a 70 dew point is sticky. If we had a 70 dew point, you'd be going, man, it really feels humid outside. And so there's lots of energy, lots of moisture in the atmosphere. And to make thunderstorms, we need heat and we need moisture, and we need that to be contrasted to the conditions aloft. So let's say something on our day forces the air to come up, whatever that is. A south wind is coming together into a north wind. Where would that happen at, do you think? Near a coast? That would. That's called a sea breeze. If it's just totally driven on the coast, it's just the wind shift that happens between having the warm land next to the cooler water, and you set up a little zone where the air comes together. What other stuff happens that we see? You guys see this on weather maps all the time if you watch any TV weather, look at any weather charts.
Cold front?
Cold front, warm front, stationary front, anything where there's a difference in the air mass that can cause the air to come together. So in this case, the north and south wind come together. Where's it going to go? Can it go into the ground?
No.
So it's got to go up. Yes.
Isn't that how the storms are formed?
That's-
Cold front and a hot front collide?
Well, it doesn't really have to be two fronts colliding, but it happens where there's a difference in the temperature of the atmosphere across the zone. So if a cold front's moving into warm, humid air, like in our example here, that would be enough to make storms. Yes, sir.
Remind me, wasn't this the day of the tropical storm that hit Tulsa? Or is that an interesting?
This will be a different day. This will be a different day. And really, if you're thinking about the big storm, it was July day last year. There was a big windstorm. It wasn't really a tropical storm. There was a big thunderstorm that produced wind gusts to hurricane force that tore up a lot of things from Tulsa all the way down into Arkansas and really all the way to Jackson, Mississippi. It was a big deal, but it wasn't this day. So our air comes together, our north and south winds come together, and a little bubble of air rises. Well, physics tells us that bubble of air will cool off 5 degrees Fahrenheit for every 1,000 feet. You can see that there above there. So what is the temperature inside the bubble now? If it just rose 3,000 feet, it started off at 85 degrees.
68.
Yep, 70. So now we have a bubble of air that came off the ground at 70 degrees. The air up at 3,000 feet is 68. What happens to that bubble of air? I'm sorry. Does it go up or down? It goes up. Hot air balloons rise. So hot air rises. So anytime you have air that's warmer, if I could hold that bubble and I had air of 70 degrees and it was 68 in the air would go up. So now we have air that's rising. So now we have air in the clouds. That means it's saturated. That means there's humidity in the air. So saturated air cools at 3 degrees Fahrenheit per 1,000 feet. If we let the computer do the rest of the math there, you can see when we get to 6,000 feet, the bubble will be at 61 degrees. At 9,000 feet, 52. Does the bubble keep going?
Yes.
Yeah. So we're going to make a thunderstorm on this day. We were able to do that. We had the right conditions when the north and south winds met and forced the air to rise. We could make a storm. What if that air got up there and the air was, say, 65 degrees in the bubble? Can't happen. What if anywhere along that line, all of a sudden the bubble of air reaches a zone where it's now colder than the air around it?
It sinks down.
It's going to sink back down. That's one of the really challenging forecasts that we have to make as meteorologists, is to try to know, will that bubble of air get to a point where it can take off? And it's hard to do because we don't have all the data we want. They launch weather balloons in Norman and Springfield and Little Rock and Shreveport, but we don't launch weather balloons here. The weather balloons cost money, and at some point you just can't launch them everywhere. So when we're making forecasts around Tulsa, we're doing it with our best educated idea of what the year is like up there, and we're trying to get a sense for, will that bubble of air keep going, or will it hit something and just fall back down? So this is really gets to the heart of trying to make thunderstorm forecasts. So this is what happens when the bubble works. This is a nice picture of a thunderstorm. It's underneath that white bubbly cloud is the rain, the hail, the lightning, the wind, maybe a tornado. But the thunderstorm itself is basically nature's safety valve. It's where too much heat, too much humidity builds up near the ground, like we saw on our bubble, and it just rises on up. So thunderstorms are good in general because they bring us rain. They're what we need to have the rain we have here in Oklahoma. But also bad stuff happens with them too. But just to give you an idea, this is our bubble sped up and over a much larger area. So let's look at this now and see how our air goes. So now, this is what we've chatted into all the media and all the meteorologists in the area. You guys don't ever get to see this maybe, but we have an internet chat room that we're chatting to the radio stations, the TV stations, anything that we see that looks cool about the weather. So we chatted this. The air over Tulsa is rapidly destabilized, and the CAPE, that's convectively available potential energy. That's basically in our calculations. Will the bubble be warmer or not? That's we can kind of assess how much energy there will be based on the temperature difference between the bubble and the air that's up there. And our energy level went from 200 to 2,000 in the last hour. So all of a sudden we're like, this isn't quite so good now. We thought we might be okay, but here between 4 and 5 o'clock, the energy in the atmosphere over Tulsa just jumped considerably. So here's where we bring in some more technology. This is where we're running at our office, and I think we're the only weather service office to do this. We try to run 5 models each hour, but a lot of times the internet holds us back and we can only do 3. But we try to run models of the atmosphere every hour in our office, focused just in our area, and just on the idea of trying to forecast something that will always be wrong. What will always be wrong is where the tornadoes will be. There's no way to really know where they're going to be, because that's just awfully hard. The atmosphere is very complicated. But we try to run multiple models to get an idea of what's going on. I don't know if you guys want to have, you teachers want to have a quiz on the components of the models later, or we can probably skip that. But what the idea is that each model runs with different physics. Each model runs with different equations. Each model runs with different starting points, different data coming in. And we do that because we want to see if these models, starting from different directions, different angles, can come up to the same thing. It's kind of like if you talk to a Republican, a Democrat, and an independent. You know what they're going to say on most things. Each one will come from their own background, and that's what these models are doing. They're all coming from their own background. But if a Republican and a Democrat and an independent all say the same thing, how often does that happen? But when they say the same thing, it's probably important. That means they all agree. That means everybody agrees something is good, bad, needs to change, doesn't need to change. So that's how these models go. If we get all 3 models beginning to say, hey, we've got strong rotation potential in the zone, we pay attention to that. We look at that harder. We say, hey, this is something important. So you guys that like the program, you guys that like physics, maybe, hey, you're not in the meteorology part of it, but you're programmers, you like physics, you like equations. That's what our computer models are. They're the nastiest equations and the nastiest math and tons of physics all being poured in there to try to help us see what might happen next. So by 6 o'clock, I've chatted into the system. Our local models are starting to show rotating storms coming out of Creek and Pawnee counties, and they go into the zone between Bartlesville and Tulsa, and they continue moving northeast. So we've gone now where our human analysis says the instability has really jumped. Now the computer models are doing that too. So now we're become more concerned. We don't just believe the computer models because you guys ever know the phrase, ever hear the phrase when we talk about computers? If I say garbage in, what do you guys say? Garbage out. So yeah, garbage in, garbage out. So if bad data went in, bad data can come out. Same thing for the computer models. They can put out completely wrong stuff. So the human has to be there to validate that and say, hey, this is what's going on. But now we've got the computers backing up our previous concerns that the meteorologists were coming up with, that we might have a rotating storm in the area. So now it's 30 minutes later, the storm in Pawnee County is rapidly becoming a severe storm. So that's this storm here to the west of Tulsa, right there. So we've chatted, that storm is rapidly becoming severe. Low-level winds, as the human is analyzing it, are becoming more supportive of making the storms rotate. And now we believe that there is a tornado threat with any developing storm. So we went from 4 o'clock, we're going to have a quiet evening, to 5 o'clock, ooh, this is starting to look a little different. 6 o'clock, hey, we're getting concerned. By 6:30, we're telling the media, we know we haven't been talking about it, but we think we have a tornado threat now, and especially in the Tulsa area. So here's basically when 1979 meant 2016. Back in the 70s, and I showed you that one radar, it was just a black and white fuzzy picture from the 70s that showed that little hook echo. When we tried to issue tornado warnings, all we could do was go on the shape of that echo. We had no more data to look at. So we developed techniques for tornado warnings in the 70s based on the shape of things and how the shapes were changing. So the forecaster in our office who was doing the warnings that day, he basically said, everything you're telling me about the environment, this storm is acting like it's a developing tornadic storm. It doesn't have rotation in it yet. It doesn't have the things we normally look at. We're not getting spotter reports, but the shape is changing just like we were taught from the 70s. So he didn't throw away the old. He still had the knowledge of the old in his head. He goes, it perfectly matches the environment you say. Here's some of the computer model output. That's 2 different models that show tracks of strong rotation coming out of Tulsa going northeast. So without any spotter reports, without any rotation on radar, based totally on just the science that's evolving, he issued a tornado warning for the Tulsa metro area, and you see the thing that sirens are, Tulsa City, Tulsa now turned all their sirens on north of 21st Street. So this is all happening without the conventional ways to issue warnings, all because we're trying to scratch at new science. We're trying to use computers, we're trying to use the physics, we're trying to use our understanding on very small scales to come up with these ideas. So by 6:46, the tornado warning is out for the north part of Tulsa. Here comes our storm. It's a big red storm. Red's always bad on radar, but it doesn't mean that it's necessarily going to produce a tornado. 7:02, our storm is still coming along. It's got a little bit of a funnier shape in the bottom of it, but it's still not super scary. What I have here on the velocity side over here is coded by two basic color schemes, red and green. Anything that's green is air motion toward the radar that sets over here at Nino to the east of Tulsa. Anything that's red is air motion away from the radar. So when you look real closely, do you pick out any reds and greens with the storm? Do you guys see anything? A little bit. Yes, sir.
I see the little white or the black with the yellow in it.
The black with the yellow here, that's just the power that's being returned. That's how much rain and hail may be out there. On this map here, if you look, there's just a little bit of green right there, just a tiny bit. That's the first real signs that some weak rotation has started in the storm, but still not super exciting. So our tornado warning's been out now for 15 minutes. Spotters don't have anything, but someone did text me during this that one of the stations, I think Travis Meyer on Channel 6, with nothing else to say, came on and said, well, the Weather Service is running very experimental models. They think there's going to be a tornado in North Tulsa in the next 30 minutes. That's why they've issued the warning, which is kind of cool that Travis would say we've issued a warning based on all this high-tech stuff that we're trying to mess with. This is what it looked like out our office window. This with all the technology that goes on, I still ran to the window and took a picture because that's what you do. So this is what it looked like as a storm looked like this on radar. This is what's called a supercell storm. This storm has rotation in it, and you kind of get that idea. If you know it's not in motion, you kind of get that idea that the storm, it looks like it's doing this. If you hear a meteorologist say, we have a supercell storm, that means the storm is rotating as it goes up. Doesn't mean it's going to make a tornado, but it's the kind of storm that you really watch. The idea of all that is to detect the rotation somewhere up in here and be able to detect that 5 or 10 or 15 minutes before it can actually build on down to be a tornado. That's the kind of storms that give us a chance to have a warning on it. So as we look closer, now do you guys see anything different in the radar velocity on the right-hand side? What? 940? Okay. Do you guys see anything different there?
The green is grown.
The green is grown.
So that means
There's more green blotches.
Yeah, so she said there's you guys are saying there's more green there, and she knew right away that means there's more rotation there. So the very beginnings of strong rotations now occurred about 20 minutes after the warnings. This is what I looked at outside the office window. Still not an obvious tornado, but the rotation is pretty strong. So here's where we know that we actually have a tornado that's occurring. This is all the same radar data, but looking at it from the standpoint of four different elements. This is the radar reflectivity. That's the velocity with the red and green. You guys can see that better now with the red and green are together. That's where it's swirling. Down here, this little zone of blue, that's what we call dual pole data, where the radar is actually sending out a horizontal pulse and a vertical pulse. And depending on how that works and what's going on in there, we can detect debris. We can detect things that are not meteorological, that are not raindrops, that are not snowflakes, that are not hail. So we know that we have this debris signature, or at least a potential debris signature, right in the middle of the red and green, right where it should be. So we know we have a tornado. Even without extra spotter reports, the new technology lets us say we do have a tornado there, and in fact we did. Compare that to the old radar, quite a difference compared to what we have now. So the tornado gets a little bit stronger, continues to move across North Tulsa. There's what it looks like outside the office window. And the tornado went across the north side of town and eventually died. Went past south of Owasso, north of the airport, and died by Claremore. Here's the storm from this last month. So, strong tornado, it tore up buildings there in Tulsa. Why was there no real good warning for that storm? This was a totally different type of storm that produced the tornado. This was the kind of storm where the rotation all forms near the cloud. So by the time we detect it that's down near the cloud, it's already doing damage. And so with the storm that's moving that quickly, you just can't have a big warning on that. So if it'll form up higher, that gives us a chance to get warnings out. If it forms down low, you don't have as much warning. And the environment, the clues, we just couldn't pull out all the clues this time in the environment. We're studying that real hard now to see, was there something in the environment that would have tipped us off? to let us do something. So the idea of like, oh, all that fancy technology that let us see the potential developing tornadic storm last year, it's not going to be 100%. And so we're still working on that, but we still hope that we can get into that mode where we can catch more of these. Yes, sir. The sirens didn't go off because we didn't have a warning in time. The storm was moving a mile every minute. So by the time we can detect it, analyze it, talk with the city, it's moved 2 or 3 miles. It's already leaving Tulsa by the time we can detect it and see what's going on. So there was just no chance for the sirens. It wasn't a problem with the city. It was a problem just the storm developed near the cloud base and moved so fast we just couldn't do anything with it. Yes.
I think I remember this one. I was asleep and I'm deathly afraid of tornadoes. I have no idea why. And so I woke up. I'm like, is this my imagination?
Yeah, that was like one.
I was looking at the radar, and this is where I was like stupid enough to think that, oh, it's not bad. There's a tornado. I was asleep.
Yeah, it's not. In fact, I got a little thing to do with you guys. There's not just a good guaranteed everything always works. You're right. Just because there wasn't red in it, or just because there wasn't a hook echo in it. And I'll show you what the radar looked like. This is what the radar looked like. It was a big band of red coming across Tulsa. No fancy hook echoes, nothing to really be seen, and the tornado's already going on there. So if you just picked up on your phone, looked, oh look, it's just storm's moving through. That was just a very, very unusual storm. It was very difficult to deal with. So, but there's the rotation with the storm that we detected right as it formed. So again, even though there's no big swirl in the radar data, there's the red and green, there's the debris pattern. It was detectable, but just not before it was already doing damage. So we could detect it, but we couldn't do it in time to really help anybody that got close to the broken arrow. So let's do this real fast. This is a little exercise for you guys. This is what meteorologists do all the time. We start with a picture that doesn't have all the pieces to it, and we try to keep looking harder, try to get pieces out of the data. We try to keep finding stuff. What do you guys think that is?
Storm.
Looks like an edge of a storm? Okay. Any other guesses? You have one? That's a good guess. We'll see. I'm gonna keep giving you more data. This is what the meteorologist always is looking for: more data to fill in the picture. Now what do you think it is? I'm giving you 40% more data now to look at.
It looks like a man.
It looks like a what?
It looks like a man.
They say it looks like a face. You said it looks like a man. I'm sorry? Yeah. Pocahontas. She thinks it's Pocahontas. We'll see. I'm gonna give you twice as much data now.
Wonder Woman, that's what it was.
Who thinks it's Wonder Woman? How do you possibly think that's Wonder Woman? When do you think it is? So we think Wonder Woman? So is it helping to get more data? This is what meteorologists, we're looking into blurry things, trying to see if we can see patterns. You guys think it's Wonder Woman, huh?
It is!
You guys are right. Wonder Woman. How about this one?
Captain America.
Superman. You got Superman? Or Captain America. Captain America. We got Superman, Captain America, Spider-Man, cereal box.
Oh, see this coming.
All right, let's look at some more. Superman. y'all think this is Superman? Why do you guys think this is Superman? You guys haven't seen him here or nothing? Think it is? You guys notice how once you kind of caught on to the pattern, you guys were jumping to answers right away. That's what meteorologists do. When we can look at more data, when we can see more stuff, we begin to recognize patterns and we begin to look at things and we begin to see. So there's still a lot of, even though the computers are really cool and do a lot of cool stuff, there's still a lot of human recognition and data going through there. And sometimes you're presented with something and you're right, and then sometimes like, hey, I kind of thought it was that way, but it turned out to be a dog instead. So you just never know. So this was the Tulsa Tornado path from August the 6th, and Nicole actually helps put a lot of these together. And so I was going to have her just mention real quickly how we do some of that, and kind of just touch back on the GIS kinds of things that we do, and then we can take a couple questions. We're probably getting pretty low on time, but have Nicole do that. See how we do.
So when the meteorologists, we go out in the field to do those EF ratings that Steve was talking about at the beginning, we have our iPads there. We can actually take pictures of some of the damage or drop a point on a map in our program. And so that all has latitude and longitude. So when we get back to our office, we can plot all of those points. And that helps us to draw a boundary of where we think the tornado actually went. So each one of these little dots that you see up here is either a picture or a point with some data on it that says this is what was damaged. This was a tree damage here, a house damaged here, and what we thought the EF rating was at each of those little points. And so then we plot those all along the map here using GIS. And that helps us then to determine, okay, where exactly did the tornado go? What did it impact? And we can provide these maps to emergency managers, first responders, insurance agencies, and just people whose homes or businesses were impacted by this. So we put it into ArcGIS, and we can change the colors and move things around, and then we can put it on a website, and we can list all the information about the tornado on our website, and then people can go and they can zoom in on the map, and they can click on the dot, and they can see all of the information that we collected, all the data that we collected out in the field. We can see the pictures that we took, and so people can really zoom in and see how the tornado may have impacted their neighborhood or their house. And so it's kind of a neat way to be able to use technology now so that everyone can see what we saw out in the field and look at all that data that we collected to share with everyone as well. So just kind of an extra new thing that we've been doing recently in the last few years using GIS. So this is another thing that we can do. Not only do we use GIS to look at all the weather data before the weather happens, but we can also use it to help us analyze storms afterwards. We had a big flood, and we went and took pictures of how high the water was in different places and made a web page for that. So the next time it floods, we'll be able to go back and say, look, during this time when the water was this high, this is what it looked like, or this is the data we had from that flood. And so we have a reference for the next time it floods to say, hey, it's going to be bad like it was this time. So it helps us to, when we do our warnings and upcoming new weather, as well as look at what happened in the past.
So how are we doing on time? We have time for questions and some things. We wanted to talk about how technology's changed, how it kind of affects the tornado world. You guys tell us, how much time do we want to do for questions and answers? We don't want to mess up. Just a couple minutes. Anybody have any questions for Nicole or myself? You guys were a great group. You got really loud and you got really quiet. That was impressive. You in the green, and I'll get you next.
Why are hurricanes so much more common in the west and in the east part of the
You're the. She says water.
more common where? I didn't hear all the question.
In the west part of the world, like where the United States and Mexico, more than the east.
Well, hurricanes develop along the equator typically, and the wind patterns along the equator is actually from west to east. As you go further north, like up here where we live, the wind patterns are more west to east, whereas at the equator it's east to west. I might have just said that backwards a minute ago. And so what happens is storms that go across Africa, and they come across the land and they get into the ocean, and they start feeding off of all of the energy from the warm ocean waters. And then the winds then are taking it across. And so as that moves from east to west across the Atlantic Ocean, it gets more and more energy built up from the warm ocean waters. And so they get bigger and bigger typically as they move westward. So that's why they develop over on the east side of the Atlantic Ocean, and they can get stronger as they move westward. Uh-huh.
Yes.
So did the radar system from like 71 and now still use the same principle, just more refined?
It's exactly right. It's the same principle, just more computer power attached to it to be able to process more of the data. So it's exactly the same. It's a pulse of radio energy that goes out, and now we just have so much more computer power that we can put on it, that we can dissect it more, we can pull out more of the signal, and we can do more things with it and make it color, but then also find the different characteristics between the horizontal and the vertical. But it's exactly the same principle. You're right. Yes.
Are the warming of the oceans going to be affecting hurricanes that we get, and are they going to get worse?
There's a lot of research going on about that right now, and that is one theory, is that warmer ocean waters will supply more energy for storms and hurricanes to develop. The other part of that too is the wind. There's how strong the winds are and the top of the atmosphere impact hurricanes as well. And so a warming earth or warming environment can also impact those winds that may actually make it harder for hurricanes to develop. So we're still doing a lot of research. There's still a lot of unknowns on how all that's going to interact together. But there is some theories out there that people as scientists are studying to try to determine what impact a warming atmosphere will have on hurricanes.
Is it like it's an El Nino that when we have an El Nino when the Pacific waters are warmer, the Atlantic hurricane season tends to be lighter and shuts down. So yeah, it's not just one is going to automatically lead the other. You might everything's much more complicated than just one thing changing. Lots of other things change too in addition. So it's just tough to say.